So welcome to the IAMP seminar. As most of you know, this is a bi-weekly event of the International Association of Mathematical Physics. And we are very happy to have Roderich Tumulka today, who will speak about the time evolution of closed macroscopic quantum systems towards thermal equilibrium. Please go ahead, Rodi.
Thank you very much, Wojciech. And thanks to the organizers for inviting me to give this seminar. Let's see, I guess I have to click here. Let me begin by mentioning this book, which has been published recently in honor of Detlef Dürr. Detlef Dürr was my PhD supervisor many years ago, and sadly, he passed away 3 years ago. And in this book, we collected 31 articles, recollections of his work and the impact that he had on his collaborators, on his colleagues, on his former students. So I think maybe some people in the audience knew Detlef, so I wanted to mention that this book has appeared. On this slide, I put some names and faces of people who have been my co-authors on some of the papers that I'm talking about here. So many of the results that I'm reporting were obtained jointly with these people. And now let me start with the physics. So here I've put the laws of thermodynamics. The first and second law were formulated by Clausius in 1865. The energy of the universe is constant. The entropy of the universe tends towards a maximum. It would be nice to give a derivation of this law from quantum mechanics. Then later on, other people added further laws that they thought should have kind of a similar status. Let me skip the third law and the 0th law. The 0th because it was felt that this should be should logically precede even the first and the second law. And then there was another statement that people felt should even precede the 0th law, and called it the -1st law of thermodynamics, which is the statement that every macroscopic system sooner or later reaches thermal equilibrium. Okay, so this is also a statement which I'd like to derive from quantum mechanics. And actually, there's been more progress in deriving the -1st law than the second law. Now, what even the statements of these laws should be when we try to derive them is kind of maybe not so obvious. Different authors have proposed rather different statements of these laws. So here, for example, for the second law, some formulations concern only thermal equilibrium states. Others also non-equilibrium. Some are about the impossibility of certain machines. So they talk about what agents, intelligent beings or observers can or cannot do. Some concern what observers can know or not know. But I'm interested here in a kind of somewhat different kind of statements, statements that just concern what's happening, statements that say that the evolution takes place from certain states to certain other states, such as that certain physically possible states, microstates, are low entropy states, other are high entropy states, and that the evolution will go from the low entropy to the high entropy states. Even what it means to talk about entropy, there are different concepts of that. Okay, so the Shannon entropy is a quantity that measures the width of a probability distribution. Entanglement entropy measures the amount of entanglement between two systems. I'm interested here in kind of different kind of quantity. I'm interested in, well, I guess the kind of thermal entropy that Clausius meant. Now, thermal entropy doesn't mean it only concerns thermal equilibrium, could be in or out of thermal equilibrium. And following Boltzmann, this quantity should be something in the spirit of being the logarithm of the number of microstates, or Boltzmann constant times this logarithm. So in this talk, the Boltzmann constant is just set to 1. There are also different concepts of thermalization or transition into thermal equilibrium or approach to thermal equilibrium. Some authors consider a system coupled to an infinite reservoir or to random perturbations. But thermalization is not limited to open systems or stochastic evolution. Consider the following example: an isolated system, and it consists of a hot break and a cold break, and we bring them into contact. So energy will be transported from the hot break to the cold one until the temperatures are equal. And this will happen also if we just isolate these two breaks from the rest of the universe. There's a certain kind of thermalization that also occurs in closed systems. Now, that's the kind of thermalization I want to consider here. So that's kind of separate from questions what happens if you couple to an infinite reservoir. Now, even what it means to be in thermal equilibrium, there are different concepts for that. A thermal state usually means a canonical density matrix, rho equals normalization factor times e to the minus beta h, where beta, of course, is the inverse temperature. That's a highly mixed state, but I'm interested here in thermodynamic behavior of a quantum system in a pure state. Sasaki in one paper wrote this is kind of a strong sense of thermalization. Yes, it's this strong sense that I'm that I'm interested in here. For many years, kind of people didn't even think about this kind of question, but in recent years that there's been a lot of attention to this kind of idea. It's often connected with the eigenstate thermalization hypothesis, and I've put here some references. I'm sure I missed many people who contributed in this direction. I guess the first contributions, the first study in this direction of thermodynamic behavior of a closed system in a pure state can be attributed to John von Neumann in 1929 in a book by Schrödinger in 1952. There's an appendix that also has considerations in this direction. And then other developments kind of started in the 1990s. Okay, so here we consider macroscopic quantum system. Macroscopic, I don't have a precise definition for that, just let's say a huge number of particles. Let's assume that's in a bounded volume, which will have the consequence that the Hamiltonian has purely discrete spectrum. We assume that the system is in a pure state, that the state vector evolves unitarily. So script h will be the name of the Hilbert space, normal h will be the name of the Hamiltonian, and here I'm introducing some notation. So E alpha are the eigenvalues, phi alpha the eigenbases, and S of any Hilbert space will be the unit sphere in that Hilbert space. Okay, so now let's try to give a definition of thermal equilibrium. Now, even in a closed quantum system in a pure state, there are kind of two inequivalent kinds of thermal equilibrium, and both actually occur. I call them microscopic thermal equilibrium and macroscopic thermal equilibrium. Here's what they are. Microscopic thermal equilibrium means that all local observables, that is, observables that refer only to a subsystem, and the subsystem should be not too big. All local observables have the same Born distribution in psi as in a thermodynamic ensemble. This actually occurs for most psis in the ensemble by a fact known as canonical typicality, which was discovered independently by several people. Actually, I forgot here to mention Seth Lloyd, who was perhaps the first to discover it. Popescu Short-Winter have a nice, rigorous mathematical version of it. this version and that of the other names mentioned here, most of these versions start from the microcanonical ensemble. And recently, with my co-authors Stefan Teufel and Cornelia Vogel, we also had a version for a different ensemble that we regard as the quantum analog as the canonical ensemble, and which is also known as a gap measure. Okay, this is just a side remark. Now, the other type of thermal equilibrium, the macroscopic thermal equilibrium, is the following condition. All macroscopic observables have the same nearly deterministic value in psi as in a thermodynamic ensemble. I will focus on this kind of thermal equilibrium, the macroscopic thermal equilibrium. Okay, I will give more detail and definition on some other slide. So here I need to start with the macrospaces, a kind of idea that was first expressed by von Neumann, but I've also seen it in a book of von Kampen, and yeah, maybe Joel Leibowitz was also one of the first to refer to that. So this is about a decomposition of the Hilbert space into subspaces H sub nu. The idea is that different macrostates, nu, correspond to mutually orthogonal subspaces. So this is an orthogonal sum here. Okay, the H nu I will call the macrospaces. And the physical meaning should be that vectors in the same H nu should look macroscopically the same. So here's an example. Nu could be some kind of description of what the system macroscopically looks like. I gave a kind of maybe stupid example by saying between 60 and 61% of the particles of the system are in the left half of the volume. Okay, of course, if we try to fully describe everything that we can macroscopically see about a system, it would be much more information than how many particles are where. Okay, this is just a toy example. Okay, so then you may think of as now associate with this macroscopic description all state vectors that would be compatible with that description. That would be the subspace H sub nu. So now we'd like to decompose the whole Hilbert space as far as we can macroscopically distinguish different states. Of course, there's some arbitrariness in the choice of these subspaces because it's not completely sharp what counts as macroscopic difference versus microscopic. So if different physicists had to do this decomposition, they would maybe do it in a somewhat different way, but it is expected that this arbitrariness doesn't matter much, particularly matters less and less in the limit in which the number of particles goes to infinity, the dimension of these subspaces go to infinity. So for most of my discussion, I will take a kind of abstract point of view where I regard these subspaces H nu as given. The classical analog of these subspaces, of the decomposition of Hilbert space into these subspaces, would be a partition of phase space into disjoint sets that could be called the macro sets. Okay. Notation, I will write d nu for the dimension of this macro space, which should be really large in practice. These numbers are large, like 10 to the 10 to the 10, or 10 to the number of particles. I will write p nu for the projection operator to the subspace H nu. I will usually just consider one microcanonical energy shell, which means the subspace spanned by all the energy eigenstates with eigenvalues in a certain narrow interval. Here, the length of the interval could be thought of as the resolution of macroscopic energy measurements. And what usually happens in practice is that each of these H nu Okay, so usually each of these H nus lies in one of these microcanonical energy shells. So let's just focus on one particular such shell. And in one shell, one of these macrospaces will have the overwhelming majority of dimensions, and that will be the thermal equilibrium state that corresponds to this energy shell. So this is expressed here by saying the ratio of dimensions is very close to 1. And in practice, so from some examples here, I tried to calculate how close actually it will be. You see it very close. Okay, Van Neumann further suggested, talked about macro observables and suggested a particular way of thinking about the macro observables. In particular, he suggested to define the macro observables in such a way that they commute exactly. If the observables that you thought of as the macro observables don't commute exactly, just adjust them a little so they do commute exactly. Before adjusting, they should already almost commute. Now adjust them a little so they do exactly commute. Okay, let's call that rounding, this change. Some authors argue that rounding is not essential for these considerations, but since rounding makes the discussion easier, I will stick with rounding, and I will assume that the macro observables have been rounded, so they commute. Now, the eigenvalues, the spacing between the eigenvalues of a macro observable should be the resolution of the macroscopic measurement, which of course has the consequence that that these macro observables then will be highly degenerate. Eigenspaces will have huge dimensions, and the idea is that the H nu are exactly the joint eigenspaces of all the macro observables. Okay. So every macro observable is just a linear combination of the P nus. It's constant on every H nu. In particular, if we take a vector from the H equilibrium, which was the dominant macrospace, the one with the most dimensions, then there every macro observable assumes its equilibrium value, which is just the eigenvalue of this self-adjoint operator associated with the eigenspace given by the H equilibrium. Now, this is also more or less the same as this quantity, which is really the average of all the eigenvalues with weights given by the dimensions of the, or proportional to the dimensions of the macrospaces. Since one of the macrospaces has the majority of the dimensions, this weighted average is more or less just this one value. Okay, now here's my definition for macroscopic thermal equilibrium, or MATE, macroscopic thermal equilibrium, with a tolerance value delta. Okay, so here the delta should be a small number, but should still be large compared to the epsilon, which if we recall from the previous slide, let me go back to the previous slide, that epsilon is something like this. It's not hard to be larger than epsilon. Okay, so the system is in macroscopic thermal equilibrium whenever its wave function psi is almost entirely in this equilibrium subspace, which is if the weight of the Born distribution given to this particular subspace is very close to 1, closer than epsilon to 1. It's then easy to prove that most wave functions actually are in MATE, which means the following. Here, let U be the uniform measure. So this is the surface area measure times the normalization factor on the sphere. And let's just consider one energy shell. Okay, normalized uniform measure. This is here is the set of all wave functions that satisfy this condition. The statement is it's at least this value. And now if delta is much larger than epsilon, then this is close to 1. So most points on the sphere actually satisfy this condition. Most points are in thermal equilibrium. The proof is easy. So I wrote it down here, but maybe I skip it. Okay, now let me talk about thermalization, or the minus first law, the approach to thermal equilibrium. A key tool for analyzing this approach is the eigenstate thermalization hypothesis that I mentioned already. It says that every eigenvector of the Hamiltonian is in thermal equilibrium. Now, the exact statement of this hypothesis depends, of course, on your definition of thermal equilibrium. So different concepts of thermal equilibrium lead to different versions of the ETH. A strong one has been used by various authors, which has been proven to be satisfied for certain random matrices, but we need only a weaker version. We need only the statement that every eigenvector of the Hamiltonian is in macroscopic thermal equilibrium, which means it's close to the equilibrium subspace. Okay. Now, here's a mathematical statement, not very hard to prove. It says that if the Hamiltonian is non-degenerate and the ETH in this mate version is satisfied, then every initial state vector will go to thermal equilibrium in the following way. It will not just go to thermal equilibrium, will not just reach thermal equilibrium sooner or later, but also stay there for a very long time. It will not stay there forever. So if you let t go to infinity, if you look at a very long time scale, 10 to the 10 years or something, then it will go away from thermal equilibrium. And but then if you look at an even longer time scale, it will go back to thermal equilibrium. And then as t goes to infinity, it will spend most of the time in thermal equilibrium. So most of the time, so here's the precise statement. So you consider the points in time at which the mate condition is satisfied. So this set here is the set of times at which the state vector is in thermal equilibrium. You take the measure of this set, compare that to the length of the whole interval. So that's the fraction of the time that the system is in thermal equilibrium. You let t go to infinity. You get something close to 1. So this is what it means to say most of the time it's in thermal equilibrium. Okay. Again, I put here the proof, but let me skip the proof. Now, this raised the question, okay, so we assume that the Hamiltonian is non-degenerate. Yes, that's a kind of generic condition. That's generically true. We also assume the ETH. How many Hamiltonians do satisfy ETH? The answer is most Hamiltonians satisfy ETH in the mate sense that I defined before. So here's a theorem saying that. Okay, you choose some tolerances, epsilon and delta. Now here, the eigenvalues could be chosen any way, just make them non-degenerate. And now the idea is that the eigenbasis is a random orthonormal basis with uniform distribution. So here, this is the uniform distribution over all orthonormal bases. This is also known as the Haar measure on the unitary group, because the orthonormal bases correspond to the unitary matrices. Okay, so you choose this basis randomly, which gives you then a random Hamiltonian. You could also choose the eigenvalues randomly, but you could also choose them deterministically. Now, if the dimension is large enough, and if this subspace, this equilibrium subspace, is close enough to the full dimension, then the ETH with a certain kind of tolerance, okay, you have to put here 2 epsilon instead of epsilon, is typically satisfied, which means that okay, with relative to this randomness, for most orthonormal bases, it's satisfied. So this is the set of all bases that satisfy the mate ETH. If you choose the bases randomly with probability 1 minus delta, this is the case. So it's not the case for all Hamiltonians. There do exist exceptional Hamiltonians that don't satisfy ETH. For example, often non-interacting Hamiltonians do that, or those with Anderson localization. That's where you can find Hamiltonians that don't do it, but most do it. Okay, here's a concrete example of a Hamiltonian satisfying ETH due to Haltasaki and his collaborator Shiraishi. Okay, again, you have to choose some tolerances. In this example, one considers n fermions on a one-dimensional periodic lattice with L sites. So the Hamiltonian, they're not interacting, no interaction between the fermions. So the Hamiltonian is the discrete Laplacian. Now here, a non-zero magnetic field through this ring on which you can, so you can think of this this lattice because it's periodic as arranged in a ring, and then a magnetic field through this ring would give a we would change the Hamiltonian in such a way that the degeneracy is removed. And now for a particular example of a subspace that could count as the equilibrium subspace. Of course, this is a simplified model. So here, the equilibrium subspace is considered as the space where the particle number in the left half of the lattice is approximately 50% up to this tolerance. And then if the relevant numbers, number of particles, number of lattice sites are sufficiently large, and under some technical assumptions, this Hamiltonian satisfies ETH. And will have the consequence that every initial state vector will sooner or later go to thermal equilibrium. Now, what happens for most Hamiltonians is even more extreme. Every state vector, or most state vectors, go to thermal equilibrium in an extremely fast way. So let's assume again that the eigenbasis of the Hamiltonian is chosen randomly with uniform distribution. And suppose we start in some initial macro space, nu0, that's not equilibrium. Then with high probability with respect to this random Hamiltonian, most initial states reach mate in a very short time of this order here, which kind of for practical numbers would be 10 to the minus 13 seconds. Now, we all know that your coffee will get cold, but not in 10 to the minus 13 seconds. Okay, so this doesn't happen in reality. What does that mean? This shows that such a random Hamiltonian is not realistic. The actual realistic Hamiltonians are not like these random Hamiltonians. The class of random matrices for which the eigenbasis is uniformly distributed over all eigenbases includes in particular the Gaussian unitary ensemble, but also you can also weaken the assumptions of this theorem. Also, Hamiltonians satisfy a strong version of the ETH that I mentioned earlier. They also display this ultra-fast thermalization. So what's the reason why a randomly chosen Hamiltonian has this behavior that realistic Hamiltonians don't have? The reason is that these random Hamiltonians with uniformly distributed eigenbases, they provide transition elements for any state vector, any direction in the Hilbert space to go directly into thermal equilibrium without passing through other macro states, such as slightly colder coffee and slightly warmer environment or something like that in between. So the reason this doesn't happen in reality is local conservation laws. So if in the thermal equilibrium state, the energy is uniformly distributed over a certain region, then in order to get to thermal equilibrium, you would have to transport the energy there, and this takes some time. In reality, because of local conservation, because you can't just beam the energy or particles from here to there, you have to transport them through the region in between. That's the reason basically that that stops this ultra-fast thermalization. Now, at this point, you might get worried when the fact of this ultra-fast thermalization invalidates the whole typicality reasoning, because we considered a typical Hamiltonian, and now we saw that a typical Hamiltonian is actually not realistic. Now we consider typical something all the time. We consider typical times, what happens for most times, what happens for most wave functions, etc. Okay, so how reliable is that? Well, a typical time just means if you wait long enough, and then if you consider the very long run, this will happen for most times. Now, typical initial wave functions, well, in the end, it all depends on kind of whether the initial wave function of the universe was typical for its macro state, which seems to be the case. Now, at the same time, the Hamiltonian doesn't seem to be typical for among all Hamiltonians, because it has local conservation laws, whereas kind of typical Hamiltonians don't have local conservation laws. Okay, so what this ultra-fast thermalization fact really shows is that the eigenbases of the Hamiltonian and the eigenbases of the joint eigenbases of the p mu's are not unrelated. They cannot be thought of as being randomly rotated relative to each other. Now, next thing I want to talk about is the macro history. And by this, I mean kind of this kind of histogram. Okay, so at every time t, this as a function of nu could be plotted as a histogram. It gives weights to every macro state. So a general psi, of course, will be a superposition of contributions from different macro spaces. So it will be a superposition of different macro states with different weights. Okay, so here are the weights. We could plot this as a histogram. So here's an example of such a histogram. And then this histogram will be time dependent. Okay, so here's my my movie with just a few frames. Okay, so I've shown you 4 frames of a movie, time dependent histogram. Now, this actual movie here is a numerical simulation done by Cornelia Vogel. And in this, here what you see are actually these weights of a time-dependent wave function. In this example, the Hilbert space has 2,222 dimensions, and it was split into 4 subspaces that played the role of the h news. One has 2 dimensions, one has 20, one has 200, and one has 2,000 dimensions, in order to reflect the fact that for more realistic models, they have very different dimensions. So let me go back in time here. You see that up here, it says what the time is. So let me go back to t equals 0. At t equals 0, we just start with a random vector in this particular subspace, macro space. And then as time increases, what happens is that parts of the wave function will lie in other macro spaces. Now, for this example, the Hamiltonian was chosen randomly to be a band matrix a random band matrix in the bases of in which the p-news are diagonal. So in the bases aligned with the macrospaces, it is a band matrix. The entries were chosen randomly. That is, they were chosen large near the main diagonal and small far away from the main diagonal. Okay, so that will cause the state vector psi to evolve from one subspace to another. Okay. Now, as we increase time, kind of more and more of the wave function accumulates in the largest. Now, in this case, the largest subspace has 90% of the dimensions, so the epsilon is not very small in this example. So we showed, I mean, in the theorems you've seen before, we've seen that for small epsilon, then kind of if you wait long enough, then kind of almost everything, like 99% of your wave function will be just in this column here. Now, okay. Now, kind of looking at these histories, these time-dependent histograms, that leads to a lot of questions. So one statement I'd like to make here is dynamical typicality. That's the following statement. Okay, so some kind of different versions of the statement have been discussed in the literature. Here I give some references. Oh, by the way, these numbers, they're always archive numbers. And archive numbers, I mean, these things have been published in some journals. Nevertheless, for easier references, to make it easier for you to look it up, if you'd like to, I gave the archive number for those articles that are available on the archive. Okay, and you can then also see which year it was. So this was 2009, this was 2018. Okay, here I present only a simplified statement of dynamical typicality, and the statement is this. Most initial state vectors from a particular macro space have the same macro history for a long time, not forever, but for a long time interval. So that means in this example, for this movie, let me go back here. What we did was we chose the initial state vector randomly from this subspace H2, and then we evolved it in time. And the statement is the picture would have been the same if we did it over again and chose a different initial state vector, but from the same H2. Okay. So here's a precise version of that. So here's the quantity that gives kind of the typical time-dependent histogram. If you start in H nu 0, then as a function of nu and t, here is what it is. This is actually the expectation value. If you choose the initial state vector psi 0 according to this distribution here, so the wavy line means has this distribution uniform in the unit sphere of this subspace. And so if you compute this expectation value, you get this value. And the statement here is that for most psi's in this macro space, the actual history will be close to the average history, provided that the okay, you want a small epsilon, but then you have to make sure that your dimension of this macro space H nu 0 is sufficiently large to make this right-hand side small. So here's a statement that is for every individual time. If at any particular time t, you consider this, you have kind of small deviation and small error. You allow epsilon errors. You could also consider a whole time interval at the same time and ask, okay, what's the, let's say, the L2 norm of the deviation? You get a similar bound.
Brody, can I ask a question? So in your numerical example, I think your d nu note is not necessarily small. No, not necessarily large, right?
Right. In this case, it was just 20.
And do you see this dynamical typicality in the new node equal 20 case, or you don't?
Yes. Let me show you a picture. So here's a picture of that. What you see here is the time evolution up to time 25. And now here, you see for the same psi, well, there are always 4 different values at every time. And these 4 different values are here drawn in different colors. Okay, so what you see here always in black is the average value that we call W on the previous slide. What you see here in blue for a particular subspace, so this is for the third macrospace, the actual value that comes from this particular realization, from this particular choice of a random initial wave function. So what you see here is that yes, the actual value is kind of stays close to this to the black curve, but it's not exactly on the black curve. There are deviations. So you can see in this example that there are deviations, and then the theorem on the previous slide tells you something about how big these deviations are.
So does this factor, I forgot, but 1 over square root b new node? Yeah, is this upper bound consistent with this error bar you see or fluctuation you see?
I think it is.
Okay. Thank you.
You're welcome. Okay. In addition to that, we could also show more. So this numerical simulation that was for a random Gaussian band matrix. Let me go back 1 page. This theorem was completely general. Didn't actually assume anything about the Hamiltonian. What was assumed here is that the psi naught is uniformly distributed from the unit sphere in this subspace. Now, if we pick a random Hamiltonian for a random Gaussian band matrix, we can also show that also the relative errors are small. Let me go back 1 page. So here is the error, the difference between the 2 quantities. This is the absolute error. Now, if this W is itself small, then of course what you'd like to have is that the error is even smaller than the W. Okay, so you'd like to have a small relative error. Yes, we can also show that for a certain nice type of matrices, random matrices, we can show that with probability close to 1. Also, the relative errors are small, and we can thus cover also the case of small w's. Okay, now the next question is about the long time behavior of this histogram. Okay, let me go back a few slides. Okay, so this was the last slide about the histogram. And from this approach to mate, we know that at least if the largest subspace has 99% of the dimensions, then in the end, kind of this column here will dominate the other columns. We already see this see a tendency in this direction here in this picture. Now, the statement I want to talk about is that for most times in the long run, there's a kind of typical picture what this looks like. Yes, it's not just that this column is then the dominant one, but we can also say something about how big these other columns are. Okay, so here's the statement. Let me start with the simplest case, but not the most general. Okay. Well, first, let me make this observation that if we just pick a psi randomly from the whole Hilbert space, then the associated histogram will just be with okay. It's not strictly correct to put here an equal sign. I should have said approximately equal. So with high probability, most psi's have approximately this histogram. So this is kind of the typical histogram. It's kind of the normal histogram that would happen for kind of an for any old state vector. Von Neumann, in his very early paper, proposed to take this as the definition of thermal equilibrium. He suggested that thermal equilibrium, so unlike what I told you about thermal equilibrium, the MATE, whose definition is that 99% are in the rightmost column, his definition was in every column, the height is proportional to the dimension of the subspace. Okay, so here I allow myself to disagree with von Neumann. This kind of behavior is not really thermal equilibrium. It's a different kind of equilibrium. I like to call it normal equilibrium. It's a kind of equilibrium that does occur. So state vectors go to normal equilibrium, even though it's not kind of the physical meaning of this normal equilibrium is not the same as thermal equilibrium. Okay, so here's a theorem saying that this normal equilibrium occurs. It was partly done by von Neumann and partly done by us. So von Neumann's proof didn't cover all relevant cases. It had kind of some technical assumptions that were, in some cases, too strong. Okay, so in this theorem, it is again assumed that that H is a random matrix with uniformly distributed eigenbases. Okay, and then the statement is you start with any wave function. Now note this is very different from saying for most wave functions, because most wave functions are kind of in thermal equilibrium anyway. But if you're allowed to start with any wave function, it could be really far from equilibrium. Okay, so this can be a non-equilibrium wave function. And then the statement is, for most times in the long run, the histogram will be close to this histogram. You see here the epsilon is small, or you can make it small. And then, so this is kind of the typical, so the histogram that's typical in the sense that it will be what the actual histogram looks like at most times, agrees with the normal histogram. Okay, that's why we call this statement normal typicality. Now, of course, this was under assumption that the eigenbase is uniformly distributed. I already said before that a uniformly distributed eigenbasis is kind of unrealistic. It leads to ultra-fast thermalization. Okay, so let's move away from this unrealistic assumption. And then here's a generalized version of this statement that applies to arbitrary Hamiltonians. Okay, so this is a more recent result here from 2022. The result still says that every initial macrostate has a typical long-time histogram, but now it may depend on the Hamiltonian and on the initial macrostate. So that means in this time-dependent histogram, then in the long run, for most times, it will be this always the same histogram, time-independent. That's why the right-hand side has no t-dependence. Okay, so that's the typical long-time behavior. Also, it doesn't depend on the, or it doesn't depend much on the initial wave function. Most initial wave functions from this macrospace behave in this way. Of course, I already said there's dynamical typicality. So most wave functions from this macro space behave the same way anyway, so it's not a surprise that also in the long run they will behave the same way. So here is the formula for this typical value. It can actually be obtained as the time average of the ensemble average. So ensemble average here means average over the unit sphere in this macro space. And here the pi e are the projection operators to eigenspaces of the Hamiltonian. The p's, as always, are projection operators to the macro spaces. Okay, so statement again, for most initial wave functions and most t, the deviation of this actual quantity from this typical value is bounded by in some way, okay, and if you make your d nu 0 large enough compared to your epsilon and delta and your degrees of degeneracy, then the right-hand side will be small and you have small deviation. Okay, now entropy and the second law. Okay, so here is how I'd like to define entropy. I said the logarithm of the number of microstates. So here, any macrostate, nu, corresponds to this macro space in Hilbert space, and kind of what plays the role here of the number of microstates is, well, the number of linearly independent vectors you could have there, the dimension. So we say the Boltzmann entropy or quantum Boltzmann entropy of a particular macrostate is the logarithm of the dimension of this macrospace. I found in a paper by Albert Einstein already a phrase that kind of goes in this direction. In 1914, at a time when people didn't even have quantum mechanics, more recently, I think the oldest references for this kind of point of view I could find were these, and a discussion of the consequences of this definition is given in this paper here. Let me point to one particular property of this definition. You see, if the equilibrium macro state corresponds to a macro space that has 99% of the dimensions, okay, then the log of d nu will be close to the log of the full dimension of the energy shell. So this explains why it's often appropriate to compute the equilibrium entropy by just computing the logarithm of the dimension of the full energy shell. Now, this definition brings us into the following situation. Entropy values here are associated with macro states, not with wave functions. Now, a general wave function is a superposition of contributions from different macro spaces. So there is no definite value of the entropy. I'd say you should regard it as being in a superposition of different entropy values. I think you should resist the temptation to ascribe any definite entropy value to that state vector or wave function psi. You should just leave it like that and say it's a superposition of different entropy values. You may think of Schrödinger's cat, which is a superposition of two different macro states. And let's say the state of a dead cat may have a higher entropy than the state of a live cat, and that's just what it is. Okay, but then what does it even mean to say that entropy increases with time? That's not obvious. Some authors have considered the average entropy. So you take for each nu, you take the Boltzmann entropy, and then you have weights for the different macro states. You just form this weighted average. But I think actually we don't want the average. We want the entropy in our branch of the wave function. In particular, if the if the average entropy increases, that would still allow that in some branches of the wave function, the entropy decreases if at the same time in other branches it increases by a larger amount. No, that doesn't sound like the kind of statement that we have in mind when we talk about the second law. Okay, so okay, new attempt to formulate what we mean by saying that the entropy increases here. So at this point, the foundations of statistical mechanics touch the foundations of quantum mechanics, and orthodox quantum mechanics is too vague to give a good answer to that. Now there are different proposed alternatives: many worlds, spontaneous collapse, hidden variables such as Bohmian mechanics. These views could provide justified answers to what we mean by entropy increase. Let me just say what the situation would be in Bohmian mechanics. In Bohmian mechanics, particles have actual positions. Actual positions does not necessarily mean, does not necessarily define an actual macro state, but in practical cases, actual particle positions will pretty much single out an actual macro state. And then you can ask, since the trajectory of these particles is random, you can ask how much probability gets transported from one macro state to another, minus the amount transported the other way. So that's what I mean by the net amount. And well, it's hard to prove, but it sounds plausible that this quantity should agree with the probability current of standard quantum mechanics. Now, in standard quantum mechanics, there's a with the Laplace operator, there's a formula for the probability current imaginary part of psi star gradient psi. Now here we need a discrete version, because now we're associating probabilities with just discrete points, the n's. Okay, and then the appropriate discrete probability current would be this expression. So this is the discrete analog of the formula for the quantum probability current that is consistent with the Born rule. Okay, so then the statement that that entropy increases with large probability, with probability close to 1, would amount to the statement that this current points overwhelmingly from the smaller macro space to the larger macro space, the one with a higher dimension, corresponding to an increase in the dimension, at least up to the time scale on which we reach thermal equilibrium. Or maybe a weaker version, you see, that would be nice to derive. That's something I would like to derive from quantum mechanics or Bohmian mechanics or some version of quantum mechanics. Here's a somewhat weaker version that would still be very nice to derive if the for kind of realistic Hamiltonians and macrospaces, if the way the histogram changes with time is up to small errors by moving to the right. Now, recall the movie that I showed you about these histograms. In these histograms, kind of mass was almost exclusively moving to the right. Well, sometimes there was a little mass on the left, so that was the exception. Most of the mass went to the right and further to the right. Now, in this example, I had ordered the macrospaces by dimension and therefore by increasing entropy. So going to the right means increasing entropy. Okay, so this is kind of the open problem. I still have 2 slides about Van Kampen's hypothesis that could provide a way of addressing this problem, but I see I'm running out of time. So let me just close here. Thank you for your attention.
So thank you very much for this beautiful talk. Are there questions, comments? So please just unmute yourself and ask.
I have a question, if I may.
Yes.
Where's temperature in your formalism? Usually would think what is the equilibrium state should depend on temperature, right?
Right. So the temperature would be connected to the energy. So the okay, so maybe let me go back.
So this is basically microcanonical, right? So
Right. So here on this slide, I mentioned canonical typicality, but I didn't write down what it was. So canonical statement typicality is the statement that for most wave functions from an energy shell, the reduced density matrix of a subsystem is approximately a canonical density matrix. That means that for the for a subsystem that's coupled to some environment that could serve as a heat bath, the density matrix of that subsystem, the reduced density matrix, is more or less a canonical density matrix, as I had written down here. So the subsystem looks like a thermal state, actually not because its wave function is random, but because it's entangled with other parts of the system. So here, you see the temperature coming in. It's here in the beta, of course. Beta is 1/T, and the appropriate value of beta and therefore of the temperature is connected to the energy of this microcanonical energy shell together with properties of the Hamiltonian. So it could be computed. You get some relation then here between the beta and the energy.
But your splitting of your Hilbert space into the H news, that is independent of temperature, right? That is just, you pick your splitting as you want, and then the thickest one you call your equilibrium macro state.
Right. The biggest one will be the equilibrium macro state. And then for this, there will usually be one particular value of temperature that would be the appropriate value of temperature. It could, for example, manifest itself by looking at a subsystem of the whole system and ask, okay, what will be the reduced density matrix of that subsystem? It will have a particular value of beta here. And that is how, once you fix your energy shell and fix the Hamiltonian, how you could see temperature arising as a kind of in the behavior of that quantum state.
Okay, any other questions? Okay, I can see that somebody's raising hand. Please ask.
Hi, Roddy. Very nice talk.
Thank you.
I was thinking about the eigenstate thermalization hypothesis proven for most H random Hamiltonians. And it was mentioned that ultra-fast thermalization shows that this may not be realistic. Random Hamiltonians don't satisfy the local conservation laws. But I was wondering, just in the case of, say, other typicality theorems, can we restrict it to the class of Hamiltonians that have the right properties, satisfying various local conservation laws, and consider typical Hamiltonians in this range, a very small atypical class, but typical members in this atypical class? And what might happen for those things and properties of?
I think that's in principle possible. I'm not able to pin down kind of what exactly the class would be, what exactly the relevant typicality measure would be. So kind of for concrete models, we've made some model assumptions, like choosing random band matrices, but these were models kind of chosen in such a way that you could mathematically analyze them. Okay, so they're intended to be simple, highly simplified. I'm not aware of any proposed class of Hamiltonians or distribution over Hamiltonians that would kind of capture which Hamiltonians are realistic candidates or look like realistic Hamiltonians. But maybe that's terribly complicated. Maybe that's too hard to do. But I'm not aware of any any compelling reasons that would make it impossible. So I don't really know whether there is a good candidate that of such a typicality measure that would kind of stand out as the most natural choice. So far, all the choices that have been made in models, as far as I'm aware, are just kind of simple, also in some way or another unrealistic attempts to model the Hamiltonian.
Right. The reason I'm thinking about this is that the typicality over Hamiltonians feels a bit different from typicality over states, phase points, or wave functions. Hamiltonian is a law governing how things move, where states are describing how things possibly are. And the typicality measure over possible laws, initially, I think conceptually, is very different kind of object. We think the law of nature are very, very special, simple, and so on, various conservation properties. So yeah, so there is this analogy conceptually, but it's surprising mathematically. They give you different, similar kind of mathematical structures, different measures, but similar kind of ideas here.
Yes, let me react to that. So even if we had reasons why the universe has to have a particular Hamiltonian, if kind of some considerations of symmetry and other things lead us to a particular, let's say, simple formula for the Hamiltonian of the universe, still it could be the case that for some respects, like kind of thermodynamic behavior, it doesn't really matter what exactly the Hamiltonian is, or the specific form of the Hamiltonian does not lead to very special behavior, but that this particular Hamiltonian behaves like any old Hamiltonian. And then kind of it could play a role in considerations to say, what is kind of the normal kind of behavior that you would see for most Hamiltonians.
Right. If
So
I just follow up with one thing, which is this is similar in some way to the quantum state universe. Some suggest and some like to think that the quantum state universe is like a law of nature, might be simple and compelling of some form, but it is still useful to consider typical wave functions of certain sort so that thermodynamically it's not too special. Or maybe that we can prove theorems that are easy to computation and I understand the behaviors without relying on the special feature of the actual wave function of the universe. Is it similar in that direction?
Yes, I think also there one could apply the same reasoning, yes.
See, yeah, thank you.
Okay, any other questions or remarks?
Yes. So yeah, I have several questions, but let me make a rather obvious comment about this entropy consideration. So you're sort of trying to define entropy for cat states, right? So, well, for me, entropy is a kind of macroscopic quantity. So I'm satisfied to define entropy only for states which have some classical meaning from macroscopic point of view. Then is it clear? Is it true that this definition, your definition of S nu, is just sufficient for a person like me, who is satisfied only with macroscopic entropy?
I think that this definition is exactly of this kind. You see here the kind of the macroscopic states.
Right. So why you are not satisfied with this?
I'm satisfied with the definition, but what I'd like to have in addition is I'd like to have a statement and the derivation of the second law. So I think this is the right definition. Now it's kind of now the question arises: what exactly is the statement of the second law, and can we derive it from?
Yes. Yeah, but you know, if you
So-
start from specific nu, like nu zero, and in the long time limit, if you end up with a single nu, which is equilibrium, then if you compare the initial state and the final state, you have macroscopically definite states, and your entropy increases. So I'm basically satisfied.
What about the time in between? So usually we would think that also in between, entropy increases step by step. So for example, I mean, extreme example would be consider the universe as a whole. There was the Big Bang, that's the initial state. Then maybe at some point in time, the whole universe will be in thermal equilibrium. In the meantime, we're in between. And we think that kind of the irreversible processes are going on all the time. Our coffee gets cold, and etc. And all of these irreversible processes, it seems, are somehow connected with entropy increase. So it would be relevant to have statements about how the entropy increases in between the initial time and the final time.
Oh, okay. Anyway, I think I have a different philosophy, but I understand what you're saying. Thank you. Yeah.
Okay, any other questions? Well, maybe let me try to ask a question. So when I hear thermalization, then my first thought is some open quantum system, like a spin boson model where you have a small system interacting with radiation, and then with a lot of effort you try to prove that a generic state under time evolution will converge to a thermal state. There are this sort of results, and this has a completely different flavor than now your approach, where I understand all Hilbert spaces are finite dimensional, the time evolution probably almost periodic, and you try to live with this recurrence, going away from equilibrium and coming back. But is there any possible connection between the two philosophies or approaches, or there's two completely different corners, say, of mathematical physics?
I think they are connected. For example, let me draw a diagram here. Okay. Let's say we have the time axis to the right, and then entropy kind of increases here, reaches a maximum, stays for a long time at the maximum value, and then kind of after a very long waiting time goes down spontaneously, and maybe then goes up again. So we have a fluctuation out of equilibrium, and then again it will spend a very long time again at the maximal value. So this, let me write here. So here we have the entropy axis is upward, the time axis is to the right. Okay, so this would be the kind of behavior that we would expect of the entropy of the Boltzmann entropy in this kind of bounded system, because of recurrence, as you say. We know from the Poincaré recurrence theorem that sooner or later we will have to go back to, for example, to a neighborhood of the initial state. Okay, now this is different in the setup with the spin boson model or other models where you have, for example, an infinite reservoir. There, by the nature of the model, the way it is set up with this infinite reservoir, then what happens would be basically the following. You would kind of, okay, let me say it this way. If I took my model system, which is kind of finite, and I make it larger and larger, so it becomes infinite. I take this limit, then in this limit, the recurrence time will go to infinity, and also this fluctuation time. So these kind of events will move out here on the time axis. So in this limit, I don't see them anymore, and in this limit, I see only this behavior, and that is what you see in your in this these models with the infinite reservoir. So I think that the kind of the two approaches are connected, and certain results from one approach can be translated into the other, or can be thought of as limiting cases of the behavior that you would see in the other approach. Now, okay, so 4 questions. Okay, so to me, I find questions interesting, like is it a problem that there's this recurrence? In the end, real systems are just finite and not infinite. Is there can we prove that for a finite system it actually goes to that entropy increases, that it goes to thermal equilibrium, things like that. So for questions like this, it seems that kind of the appropriate place to study these questions is for a finite system and not for the infinite one. So the infinite one, it it corresponds to a certain limiting case of the finite system. Now, in this limiting case, you won't see these recurrence events anymore. So if you want to study these recurrence events, or if you want to know what's the status of these recurrence events, then that's a reason for sticking to the finite system.
Okay, I see. Thank you. Any other questions? Yes, please.
So here is Jakob Ingvarsson. Can you hear me?
Yes, I can.
Okay, so thank you very much for this very nice and informative lecture. I have 2 questions or comments. The first is, this is all, of course, well, I say of course, but it is based on quantum mechanics. Of course, since you quoted Boltzmann's entropy, Boltzmann didn't know anything about quantum mechanics, but he could say something nevertheless. And so one question is, so has anybody looked at this in the context of classical mechanics or classical statistical mechanics? That's one thing. Another is concerning the monotonicity of the entropy and even the definition of temperature. In, well, admittedly a purely phenomenological theory, but it's, however, very important for practical uses of non-equilibrium thermodynamics. There is a complication, namely, there is no really unique definition of the temperature concept if you are far from equilibrium. And even a simple thing like heat conduction, which is in simplest case simply Fourier's law, when you when you deviate considerably from equilibrium in the initial state, you will have to take also the currents into account. You cannot just work with the phenomenological entropy, which is just a function of the density. You will have to take also the currents into account, and you will, for instance, have different heat with different equations for heat conductions. Besides the Fourier law, there is a so-called Cattaneo law. These are, of course, both phenomenological equations, but one is supposed to be better when you have large deviations from equilibrium. In that case, the entropy, for instance, depends on the currents, not only on the density. And the equation, the heat equation, is not Fourier law. Because if you would take just Fourier law and you are very far from equilibrium, you may discover that the entropy does not move monotonically from the initial value and to equilibrium. It may show real oscillations. There are curves of this type in textbooks on non-equilibrium thermodynamics. And however, if you use a different definition of the entropy, which depends on the current, you may reproduce a monotonous curve. So, well, so to say, my general question is how much of what you have been saying depends on quantum mechanics. So this is very special to quantum mechanics, because one sees if one uses a different framework, you may get something different.
Yes, so something completely analogous can be done in classical mechanics. There, let me write down the definition there. Maybe I can show that to the camera. Can you see that? So the entropy.
Yes, just logarithm of the phase volume. Yes, like
logarithm of the volume of the macro set. So that would be the set in phase space of all phase points that look macroscopically the same as each other, or that look like this macro state nu. So you would partition the phase space into these macro sets. The macro sets would be of very different size. And then for each macro state, you would have an entropy value, the logarithm of the volume. Now, a crucial difference between the classical case and the quantum case is that in the classical case, every phase point lies in one of these sets because the sets form a partition. So every phase point, every microstate has a unique macrostate, and this macrostate has a unique entropy value. So every microstate has a unique entropy value, and then you can ask the question. The question immediately makes sense whether this entropy value increases with time or not. So that's different in the quantum case. So in a sense, the quantum case is more complicated here because you can have these superpositions. In another sense, the classical case is more complicated because in the classical case, you see in the quantum case, you have a linear evolution equation. So you're just studying linear operators, or in finite dimension, you're just studying matrices. So that gives us kind of more hope that we could actually tackle the question. In the classical case, since you just have, let's say, a vector field, the time evolution is defined by a vector field on phase space. And about this, what do you know? You just know Liouville's theorem. And then it can become very complicated to say anything from that about how the phase point evolves. Now, in the classical case, it sounds somewhat believable that if you partition the whole phase space into these sets of very different sizes, and you start from a very small set, and then you move in some complicated, irregular way that is not particularly chosen to fit in any particular way with these macro sets, with these cells, that you will have and volume is preserved, then it is plausible that the motion will kind of bring the phase point to larger and larger and larger macro sets, which would correspond to increase of the Boltzmann entropy. Now, Boltzmann himself, he had this example of the Boltzmann equation. So he had the hard sphere gas. He argued that for a kind of dilute hard sphere gas with very many spheres, the behavior would essentially be given by the Boltzmann equation. If this is true, then from the Boltzmann equation, he could derive that the negative H functional, which is exactly this kind of definition of entropy here, would actually go up. So he had an example where he could not really prove, but at least make it believable that entropy actually does go up. Now, in the cases that you mentioned about the heat conduction, okay, I'm not an expert on that. I don't know the details. I've seen some examples in the literature where the question in classical examples, the question whether the entropy goes up or not depends a lot on whether you make a reasonable or less reasonable choice of the macro variables or the macro states or the macro sets. So some examples in the literature started with kind of very artificial choice of macro sets. Of course, the examples that I gave you in my talk today were also artificial. Okay, we have to study simplified models. Okay, but in some of these examples in the literature, the macro sets were chosen in an artificial way and showed entropy going down. And when people try to choose the macro sets in a more realistic way, then lo and behold, the entropy went up. So that suggests to me that maybe the question of what's a kind of realistic choice of the macro sets, maybe the question is subtle. It suggests to me maybe the behavior that the Boltzmann entropy in classical systems goes up, increases with time, is kind of robust, even though we have no kind of real proof for that. And now the question would be, in quantum mechanics, can we do better than that? In quantum mechanics, can we give a proof of the second law?
Of course, we don't even have a proof of from classical mechanics of the Boltzmann equation, except for extremely short times. Of course,
that's right. I would say at least the fact that for extremely short times it can be proved. That's kind of very nice and encouraging result.
It's very remarkable and extremely difficult, but these times are much shorter than the mean collision times. Okay, but we shouldn't discuss all this. So thank you very much for your reply to my questions.
Thank you.
Okay. Okay, I guess we should close the official part of the meeting since it's already getting late. So if there are still some questions, I guess they can be asked after we stop the recording. So let's thank the speaker again. And let me stop the recording.